Hi all. Today we would like to investigate a connection between concentration of measure or probability and what is called isoperimetry, which is a very classical subject in geometry. So this gives us a new geometric viewpoint on how to understand and approach concentration of measure results. And in fact, we will find out that results in isoperimetry actually imply concentration of measure results. So what is the high level idea behind this approach? The high level idea is that in order to control in probability the fluctuations of some function of n random variables denoted by x, where x given by x1 through xn is a random vector, it helps to view x as a point in n dimensions or in some convenient n dimensional space, so that if we understand where this point is distributed in n dimensional space using results from geometry and isoperimetry, then we will have some idea about how to control the fluctuations of the function f applied to x. Okay. So what is firstly the isoperimetry view here? So here is an example of a classical isoperimetric theorem, okay, which is perhaps a statement that you would have seen during the course of high school or college, which is regarded as a well-known fact by now. So it says, for instance, that among all shapes of the same volume in Euclidean space, let's think of three-dimensional Euclidean space as usual. So if you're given a target volume, then if you want to find the shape which minimizes the surface area with the given volume, then it has to be a sphere or the Euclidean ball more generally. Okay, so this is essentially a typical or the most classical statement of isoperimetry there is. Okay, so in some sense we are stating the dual form of the classical isoperimetric theorem. Isoperimetry really means shapes that have have equal perimeter or surface area, and the dual version of the statement is that among all shapes of a given surface area, the Euclidean ball has the maximum volume. Okay. Now there are two terms here which are very important here to understand in such a statement. There is a term which is indicative of a measure, okay, or volume, in the sense that it measures size, and there is a term that measures what is called perimeter or surface area. In some sense we will show that this can be interpreted in terms of distances. Okay. So what we need typically to frame classical like isoperimetry statements is the notion of a metric measure space. So so in all that follows, in the background we will always assume that we are working in a space that has both a notion of a metric or a distance measure as well as a volume measure. Okay. So again, coming back to a statement like the classical isoperimetric theorem, let's be a little more precise about what we mean by volume and surface area. So here, volume of a set A, let's say lying in n dimensional Euclidean space, is just taken to be its standard measure or Lebesgue measure more precisely, and this is just given by the integral of dx over A, for instance. What about surface area? So what about surface area? How do we define the surface area of a set or an object or a shape? So one of the ways of doing it is through blow-ups. So let's define for a given set S the epsilon blow-up of that set S. So note that S is sitting in a space with a metric given by D and volume measure given by wall. So the epsilon blow up of a set S is defined to be let's say notation S epsilon is the set of all points x such that the distance of x from S is at most epsilon, okay, where, by the way, what is the distance of a point from a set? D of x comma S is just defined to be the minimum distance of any point in S from x. Okay, so S epsilon is essentially capturing the set of all points which are at a distance of at most epsilon from the set S. So it's the set S with a small expansion, if you will. So for instance, in standard Euclidean space, if B is the unit ball in standard Euclidean space, that means the metric is the L2 metric, then with respect to the usual, that means L2 metric, the epsilon blow up of any set is essentially obtained by taking S and adding to it, in a set theoretic sense, a scaled multiple of epsilon times B, and this in turn can be explicitly defined as the set of all x plus epsilon y, where x belongs to S and y belongs to B. Okay. Now once we have the notion of a blow up, it's quite natural to be able to use this to define the surface area of a set S. So here's one particular definition of the surface area with respect to a volume measure and a notion of distance. So the volume, let's see, so the surface area in this view of S is defined to be the volume of the boundary of S, okay, and we define this in turn to be the limit as epsilon approaches 0 of the volume of the epsilon blow up of S minus the volume of S divided by epsilon. Okay, so what this does in pictures is that if you have this set abstractly which is called S, so how would you evaluate in some sense the measure its surface area? Its surface area is roughly the measure of this the size in some sense of this red curve, and how you measure this in some sense is to try to take a small blow up. So the epsilon blow up of S is essentially this set. The volume of the epsilon blow up of S minus the volume of S in some sense is going to be able to give us a measure of the difference area, which is the shaded area here, okay, and that's what the surface area ends up measuring. So by the way, we are not going to be technically very precise and assume that these limits exist, but one can always show that for an appropriate class of bodies or sets S, such a surface area measure is well defined in the sense that the limit exists. So again some examples. So one can use this to understand the usual surface area of sets in Euclidean space. So for the unit ball B in Euclidean space, of dimension n, the following is well known, which is volume of let us say a scaled version of the unit ball, r times the unit ball, which is basically the ball of radius r, is scales as r to the n with some constant that depends on the dimension, and the volume, the surface area of this ball of radius r, which is volume of the boundary of Rb. So recall that when we say the volume of the boundary of Rb, it's really an n minus 1 dimensional volume, which is the surface area. it's known, and this is equal to n. It's really in fact the derivative of the volume evaluated with respect to r. So this is n Cn r raised to n minus 1. Okay, and this reduces to, for 3-dimensional space, we have the usual high school formulae that the volume of a sphere of radius r in 3 dimensions is some constant 4/3 pi r cube. So 4/3 pi is basically the C of n, C of 3, and the volume of the surface area of a sphere is basically 4 pi r square. Okay. So this generalizes to any dimension n. In the standard Euclidean geometry in n dimensions with the standard Lebesgue measure, which measures volume. Okay. Next we go to investigating the exact connection between statements of isoperimetry such as this. Okay. So statements of isoperimetry will broadly be taken to mean the solution of problems where a surface area or a volume is given, and you have to try to optimize over all shapes of either the volume or the surface area respectively to find sort of optimal shapes in some sense. Okay, so that's an isoperimetry statement. What is the connection between such isoperimetry statements and concentration of measure inequalities? The basic idea here is that isoperimetric inequalities essentially in a critical way tell us exactly how much mass or probability is accumulated near the boundary of a set. Okay, so that's what an isoperimetric statement is really trying to say. Okay, so for instance, in the classical isoperimetric theorem, it's basically saying that the sphere sort of has a certain distribution of mass on its boundaries, which is optimal compared to any other body with the same volume. Okay, so towards this, let's start by defining this very key quantity or function alpha of t. So this is, by the way, defined for all t positive, or in fact non-negative, as the largest probability of a complement, at complement, where at is the t blow up of any set A, of all sets A which have a minimum probability measure of half. So imagine, so by the way, something that is useful to keep in mind is that the setting here is that of a metric probability space. So we are imagining a space that is endowed both with a probability measure uh, and as well as a metric. So here we are trying to define alpha of t as the largest probability of the t blow up of the complement of the t blow up of any set which has probability at least half for every t greater than 0, and this is also called, alpha of t is also called the concentration function. So it basically measures how much mass there is in if you blow up A by a small amount t when the set A itself is sizable. Okay, and another definition that we will often need is that of a median of a random variable. So what is the median of a random variable? A median of a random variable is any value such that the probability that the random variable is either at most that value or at least that value are both at least half. Okay, there can be many medians for a single random variable, it's not unique, but we will call M to be a median if this property is satisfied here. Okay, so yeah, now the main bridge between isoperimetry or concentration functions and concentration inequalities themselves is what is called Levy's inequality, which says that consider any Lipschitz function f with respect to the metric d. Okay, so let's say there is a metric probability space on which there is a function f defined, which is a Lipschitz function. Now by Lipschitz function, what do we mean? we mean exactly that for all x and y in the space, we have f of x minus f of y to be bounded in absolute value by the distance between x and y, the metric distance between x and y. That's what it means to be a Lipschitz function. So in fact, for any Lipschitz function, any such Lipschitz function f on this metric probability space, for all positive t, we have these inequalities. Probability that f of x is larger than uh, any median of it, m f of x plus t less than equal to alpha t. Let's write m f of x in boldface, just in analogy with expected value, even though this is not unique. And on the other hand as well, probability f of x is short by minus t, is short by t from its median, is also bounded by the concentration function t. Okay, for any median m f of x of f of x of this random variable f of x. So Levy's inequality basically says that if you can bound the concentration function, which is a purely geometric quantity, then that at once gives you concentration results of a function of Lipschitz functions about their median values, about their medians. Okay, so this is not concentration about the expected value, but this is very differently concentration about the median. Although in many cases one can show that the median and expected value are fairly close by themselves. But the natural spirit of Levy's inequality is to state it in the sense of the median, concentration about the median. Okay, so let's go ahead and show the proof of this inequality. So define A as the set of all x. Let's show the first inequality. So if you define A as a set of all vectors or points x, where f of x is at most its median, m f of capital X as a random variable, then by definition we know that the probability of A is at least half. This is by the median property. Or median definition, and then we have that the t blow up of A, which is defined as the set of all y's in the space where for which there exists an exists an x in A with dxy at most t, belongs, so this itself is a subset of all points y, where, so recall that if x and y are such that dxy less than equal to t, then so we can say that the set of all such y's is a subset of y's where f of y is at most m f of x plus t. Why is this? This is because you can write f of y minus m f of x is less than equal to f of y. So any x any such x is assumed to belong to A. So we know that for x, f of x is upper bounded by m f of x, and we can say that we can replace m f of x by f of y. We can replace m f of x by f of small x. Okay, because of precisely this reason. And we know that f is Lipschitz, so basically this is upper bounded by dxy, and we know that dxy is upper bounded by t. Okay, so this is what gives us this inequality. At is a subset of y such that f of y is at most m f of x plus t, and this in turn implies that the probability that f of x is larger than m f of x plus t must be bounded by the probability of At complement, and by definition probability of At complement can be at most its concentration function alpha of t. So we have the first inequality, and the other inequality follows in a very similar manner, and it's a symmetric counterpart of this one. So that completes the proof of Levy's inequality. In fact, the Levy's inequalities are tight in a certain sense, in the sense that there is this following converse. So the converse reads, if beta of t is another function of positive t, such that for any Lipschitz function f, where we have the same definition of Lipschitz function with respect to this metric t, if always a probability of f of x larger than its median plus t is bounded by beta of t, then beta of t must be at least alpha of t. Okay, so this theorem, Levy's inequalities are essentially tight over all Lipschitz functions f, and the reason why this is true is because of the proof of this converse, which basically says that you define this function fa of x. For any given set A, we can define a function fa of x as the distance of x from the set A. It can be easily checked that fa is Lipschitz continuous. This is a Lipschitz function, and the median of the median of fa of capital X, okay, as a random variable is 0 if the probability of the set A is at least half. Okay, so 0 is a valid median for fa of capital X if the probability of A is at least half. So for any such A, the probability of AT complement is the probability that fa of x, this is just by definition, greater than or equal to t, and we know by the hypothesis that so this is exactly p fa x greater than or equal to 0 plus t. 0 plays the role of a median, and by hypothesis this is at least beta of t, right? And so if we just take the supremum on both sides with respect to all such sets A with the probability at least half, we get therefore that alpha of t is upper bounded by beta of t. Okay, so this basically establishes the other side of Levy's inequality, and so the summary from this connection between between the concentration function and fluctuations about the median is that upper bounds for alpha of t imply upper bounds for the concentration of Lipschitz functions about their medians. Okay. Now so with this, essentially the effort shifts to trying to find good ways to upper bound the concentration function in general or given metric probability spaces. So what we know so far is that in fact if you have an exact isoperimetry theorem. So what do you mean by an exact isoperimetry theorem? It's a statement that says that in some sense, given a volume, the shape or body or subset S minimizes its surface area. So these are essentially called exact isoperimetry statements. So mathematically it has the form that there exists a B, a subset B or a shape B with probability of B at least half, such that for every other shape A with probability at least half, the volume of the blow up of A is at least the volume or probability of the blow up of B. And this in fact implies that the concentration function alpha of t can just be bounded above by the probability of the complement of the blow up of p for every value positive t of positive t. So this is what an exact isoperimetry theorem gets you. So in some lucky cases, a set like this is explicitly definable. And so here are two classical examples. The first one is isoperimetry statements of isoperimetry for the uniform measure or uniform probability distribution on the surface of the unit ball in n dimensions. So Sn minus 1 is notation for the surface of the unit ball in n dimensions. It's a set of all x in Rn such that their L2 norm is exactly equal to 1. And imagine that there is a distance measure, a metric on the surface of the unit ball. So one can have two different metrics which both work for this example. You can have what is called geodesic distance between 2 points on the surface. So roughly speaking, in 3 dimensions, if this is the ball in 3 dimensions, then if you want to measure the distance between 2 points on the surface of the unit ball, all you say is that you find the equator that connects them. So if this is the segment of the equator that connects them on the surface of the unit sphere, then the length of that segment of the equator is their geodesic distance. Equivalently, one can also use a notion of distance like the Euclidean distance to measure distance on the surface of the sphere. But in any case, imagine that there is this distance metric defined on the surface of the sphere, which is symmetric and translation invariant over the surface of the sphere, and you have the uniform probability distribution on the surface of the sphere. Okay, so that defines the metric probability space for this example. So there is a famous isoperimetry result called again Levy's isoperimetry theorem. That says that essentially specifies the sets of least volume given a surface area on the surface of the n-dimensional unit sphere. So for B equal to, let's say, all points on the surface of the sphere with their first coordinate being non-negative, which is exactly a hemisphere. So in the usual sense, this would mean the northern hemisphere, for instance. Any hemisphere will work for the purposes of this theorem. We must have that P of B is equal to half, and for all A such that probability of A is at least half, the probability of the epsilon blow up of A is lower bounded by the probability of the epsilon blow up of this northern hemisphere or any hemisphere. Okay, and this finally implies that alpha of t is upper bounded by the probability of bt complement. Okay, and one can also do explicit calculations to show that the measure of the complement of bt can be upper bounded by something like e to the minus n minus 1 t square by 2. Okay, so in other words, what this says is that if you again go back to the unit sphere in let's say 3 dimensions, so S3 is S2 is what we are talking about, the surface. So the probability, the metric probability space is the surface of the 3-dimensional sphere. Then what it says essentially is that let's say there is this hemisphere, which is let's say one hemisphere. Let's call this set B, and the probability of the complement of B so if you take a blow up, so if this is B, let's define a small blow up of it. So the T blow up of B is the northern hemisphere union the strip, which is shaded here. So go a little south of the equator. So the solid line is the equator, is an equator. If you go a little south of the equator by an amount proportional to T, there is there is very little mass in the complement. Okay, so the probability of this part, the remaining part, falls off very rapidly with T. So it's bounded above by e raised to n minus 1 t square by 2. Okay, and in fact one can run the same argument with the southern hemisphere to basically say that you could you go a little north of the equator. Okay, and whatever is the remaining mass has extremely low probability. So finally by a sort of basic probability, it says that almost all the mass is near an equator. Okay, so most of the probability mass is near an equator. And this in fact in high dimensions gives rise to very surprising consequences or non-intuitive consequences, because if one argued that all the mass there is a lot of probability mass, almost probability 1 on this equator, well you could run the same argument for any equator. So this is another equator. Okay, so this equator also has mass close to 1, probability mass close to 1, and so it must mean that their intersection also has probability mass close to 1. Okay, so essentially it means that any two equators in high dimensional spaces on the surface of spheres in high dimensional spaces essentially have a lot in common. Okay, which is somewhat counterintuitive given our understanding of three-dimensional geometry. But in any case, this is true of such metric measure spaces. The second well-known example of an isoperimetric theorem is what is known for standard Gaussian measure in n dimensions endowed with the usual metric, and we have standard normal measure, which is essentially independent measure, Gaussian measure in all coordinates. So here the statement of isoperimetry, so what are the optimal sets? The optimal sets essentially turn out to be half spaces. So take any B which looks like the set of all x's in Rn with let us say one coordinate being non-negative. This is basically a half space. So it's known, so it's obvious that probability of B is equal to half because of the definition of independent Gaussian measure. And for all A with probability of A at least half, we have that probability of A, the epsilon blow up of any such A is at least lower bounded by probability of epsilon blow up. So this is the Gaussian isoperimetric theorem. So this statement is the Gaussian isoperimetric theorem. That's the content of the Gaussian isoperimetric theorem, and as a consequence of it, we get that alpha of t is upper bounded by the probability of the t blow up, the complement of the t blow up of any half space passing through the origin. And this because of properties of independent Gaussian measure is as p of x1 exceeding t, okay, which is the probability of a standard normal exceeding a value t, which is what is defined to be the q function of a Gaussian, which can be for instance upper bounded by e raised to minus t square by 2. Okay, so alpha of t is it's possible to bound alpha of t by probability of B complement just by virtue of using this very powerful Gaussian isoperimetric theorem. And as we know, bounds on alpha of t can easily translate to bounds on the concentration of Lipschitz functions about their medians. Okay, so in this lecture we have seen how isoperimetry results or very strong or exact isoperimetry results help us to bound the concentration function alpha of t. But what if such occurrences are more the exception rather than the norm. Often it is not explicitly possible to prove such exact isoperimetry results. So what happens when we do not have access to isoperimetry results for our given metric probability space of interest? Are there other ways to sort of understand bounds on alpha of t, and that is what we will explore in the next lecture. Thank you.